Hi, my name is Nick Vitsas. I am a PhD student from the Computer Graphics Group of Athens University of Economics and Business. This is a presentation of our work on Rayground, an online educational tool for ray tracing. Ray tracing is one of the most common teaching subjects in computer graphics courses, presented as an elegant and robust algorithm for image synthesis. Undergraduate graphics syllabi are built around the rasterization pipeline and devote a limited number of lectures to explain the basic concepts of ray tracing. Inevitably, this paradigm shift requires a lot of rewiring. Graduate syllabi need to cover a wide range of advanced and diverse topics and don't have much time to introduce the basics. Both students and instructors struggle to make the quick transition from rasterization to ray tracing. After all, rasterization and ray tracing are very different in terms of mechanics, but at a high level share a large portion of computer graphics theory. Recent advances indicate that ray tracing-based methods can be further adopted and integrated into computer graphics courses at all levels. Unfortunately, this trend is not backed by widely available educational tools that improve the learning curve and support the newfound popularity of ray tracing. Recently, there has been a rise in learning material related to ray tracing. Two successful examples are Peter Sillery's Ray Tracing in 1 Weekend series, which introduces the basics with a mentality of getting you to a cool program as quickly as possible. Then, for a full journey from theory to implementation, physically based rendering of the book has been a staple in recent years and has recently been made available online. However, such solutions lack interactivity and do not provide easy prototyping capabilities. The improvements in hardware are also backed by software solutions, with ray tracing rapidly being introduced in modern graphics APIs. The question is whether these APIs are ready to support computer graphics courses. They are very low-level and complex APIs. This is understandable, as they have to squeeze every last bit of performance out of the hardware while remaining flexible and configurable. They are therefore not suitable for introductory courses. Also, implementation maturity varies across devices, and especially state-of-the-art ray tracing features are not widely supported. More often than not, these APIs or frameworks are heavily dependent on very specific software and hardware. Not to mention that all this flexibility and performance comes at the cost of long and complex installation instructions where you need to potentially support multiple API versions and maintain a large dependency tree. A CPU framework could be developed, but it would be very slow on commodity hardware and would require significant effort to remain cross-platform. And just as we thought that we were running out of options, we considered the World Wide Web. It is by far the platform with the biggest outreach, so it is a great choice for the deployment of educational tools. The sandbox environment in modern browser is perfect for a consistent and secure platform that automatically gets updated. It is grounded on a series of international open standards with wide adoption and has had access to GPU computations through the WebGL 1 and WebGL 2 standards. Of course, not everything is perfect. Ray tracing is a computationally demanding task. There is no functionality exposed in any modern web standard that can accommodate ray tracing acceleration. Even the WebGL spec is very limited in terms of general-purpose GPU computing. Also, having a sandbox environment that puts security, stability, and cross-device support first means that you have to make sacrifices both in terms of flexibility and performance. We're definitely not the first to see this opportunity. There have been many successful examples of online interactive tools for computer graphics. ShaderToy is a widely popular platform for experimenting with fragment shaders and screen space effects that has also been used for ray tracing, albeit with procedural geometry and within a fragment shader. Babylon.js, a popular JavaScript graphics library, has a playground for rapid experimentation with graphics in an online IDE fashion. Examples like these motivated us to pursue a similar online tool specifically targeted to ray tracing. We set a series of goals and non-goals. We wanted a highly accessible platform that could run on a wide range of devices. We emphasized on the concept of rapid prototyping, quick to set up, easy to experiment. Use the tool to improve both lectures and lab courses. Encourage gradual self-study. Ease of remote teaching was also a major concern. Ensure as smooth a transition as possible from rasterization to ray tracing. Demystify ray tracing fundamentals through a programmable graphics pipeline of distinct configurable ray tracing stages. We wanted a modern API that would be familiar to experienced users and easy to pick up for newcomers. Our non-goals were much simpler. We understood that we could not develop a tool that could completely replace modern rasterization-based APIs. We did not have the intention of offering a fully featured API for programming ray tracing algorithms. This would have definitely gotten in the way of simplicity and smooth transition. To a large extent, we achieved our goals, and Rayground is a ray tracing prototyping tool on the web that is open, cross-platform, and available to everyone. The platform is hosted on rayground.com and works on any platform that has a WebGL2 compliant browser. Let's discuss the ray tracing pipeline that Rayground exposes. As mentioned before, we wanted our API to closely match the design of other modern ray tracing pipelines. Everything in computer graphics begins with the definition of a scene. Next is the phase of generating primary rays and submitting them for intersection with the scene. The next step depends on the results of the intersection. Rays that do not intersect the scene trigger a miss event, and rays that hit part of the scene's geometry generate a hit event. Whether the ray triggers a miss or a hit event, a recursive step begins where new rays can be submitted for intersection. Commonly, this recursion breaks after a predetermined amount of steps called the recursion depth. After the recursion depth is reached or no rays are submitted, the pipeline switches to the accumulation stage. Here, the calculated results of the current pipeline execution, which most times it's simply the pixel's color, are blended with the results of previous pipeline executions. The accumulated values are submitted to a post-processing stage where final filtering is applied to the accumulation buffer, and lastly, post-processed values are submitted as RGB color values to the frame buffer. The question that is raised naturally is which of these steps should be programmable. To maintain simplicity and in accordance with modern graphics APIs, we came up with the following programmable pipeline. 1 declarative stage for scene specification and 4 programmable stages for supporting a wide range of ray tracing based algorithms. In this pipeline, user code is provided for each programmable stage and is called every time the relevant event is triggered. Since we are using WebGL, the programming language is the familiar GLSL language. We do not expose the internals of acceleration data structures to the Rayground developer for simplicity and future-proof code design, since the internals of the ray tracer are likely to change. Similarly, for the accumulation operation, which is fixed to additive alpha blending. So, we have the following configurable stages: scene definition, where the user specifies object properties and global simulation settings, ray generation stage for primary rays, miss or hit stage, where intersection data become available and new rays are spawned into the scene. The post-processing stage, which completes the image synthesis for the current rendering frame. Here's a quick reference to the Rayground API. The specifics of each variable do not matter here, and we only want you to get a sense of how the API is structured. We wanted students to feel right at home. We wanted to map fundamental concepts of ray tracing to a GL-like API. For example, rays are submitted for intersection by assigning to the built-ins RG ray direction and RG ray origin. Also, during the hit stage, the user is expectedly given access to built-in variables that hold the normal position, material ID, and other intersection-related values. The scene is described using a simple custom JSON format. The inputs required are simulation settings and object geometry. The most common simulation setting is that of the recursion depth we discussed earlier. As for objects, we made sure to add support for basic 3D shapes which are positioned in the scene using a transformation, rotation, and scale triplet. Per object material properties are also supported and become available at the heat stage for use in local shading. During ray generation, the user submits a code snippet that executes in parallel for each pixel. Given the pixel's coordinates and canvas dimensions, one can generate rays from a virtual camera. For flexibility, each ray carries a user-assignable payload and accumulation value. A ray is submitted in code by setting the built-in variables RG_RayOrigin and RG_RayDirection. Ray payload and accumulation are initialized through RGPayloadX and RGAccumulation. It is easy to think of each ray as carrying a struct of the form showcased in the lower right corner of the slide. Submitted rays are consequently intersected with the scene, and the framework triggers a miss or a hit event accordingly. This is where local shading commonly takes place. Visibility queries are also very useful in this stage and can be performed using the RGTraceOcclusion API function within the shader. Secondary rays are submitted in code, again by assigning to the built-in variables RG_RayOrigin and RG_RayDirection. Ray payload and ray accumulation are further updated through RGPayloadX and RGAccumulation. These newly submitted rays are in turn intersected with the scene, potentially triggering new miss or hit event. A pixel shader's execution only stops when the max depth iteration is reached or each ray is set to inactive. Here's a preview of some of the built-ins exposed through the API during hit events. These are the values after the first bounce event. They are useful for appearance shading and next event estimation. The miss event type does not expose any geometric properties but is used for background coloring. Finally, after the recursion depth has been reached and accumulation has taken place, the user gains random access to the accumulation buffer in the final post-processing state. All sorts of filters can be applied here, some relevant to ray tracing in particular, and some relevant to computer graphics in general. Rayground's design had teaching at its core, and for the time being had to coexist with a rasterization-based teaching solution. Through rapid prototyping, high interactivity, and familiarity offered by GLSL, it's a perfect fit for the introduction of ray tracing after spending time in courses in order to teach OpenGL and the standard graphics pipeline. We considered Rayground for interactive lectures, lab coursework, live examination, exercises, self-study, and more. We designed coursework using Rayground for both undergraduate and graduate courses. For the undergraduate course structure, to facilitate the inclusion of a new tool alongside a standard rasterization-based framework, we abstracted the rendering pipeline. We divided it into 4 generic stages: geometry setup, sampling or fragment generation, shading, and compositing, so that they could be independently mapped to rasterization or ray tracing accordingly. This allowed common topics to remain separate from the underlying pipeline. Topics such as material properties, local shading, geometry representation, texturing, image domain sampling, anti-aliasing, etc. The actual lectures were enriched with interactive demonstrations of ray tracing concepts using Rayground. Implementation and theory could now walk hand in hand. This prompted more students to actively participate and helped them quickly correlate presented concepts with their practical implementation. As is common, our computer graphics lectures are supported by a series of practical exercises in a lab. We have 5 labs devoted to rasterization, 2 to ray tracing, and 1 for assignment-related topics. We had a lot of ground to cover for the 2 ray tracing labs. Here is how we structured them using Rayground. Lab 1 had an introductory 1-hour session where we familiarized students with the Rayground interface, explained the programmable pipeline, and the scene definition format. We would then set up a simple orthographic camera and introduce the basic object properties provided by the Rayground API. We then introduce image synthesis using ray tracing. A perspective camera is set up. Direct lighting from point light sources with visibility queries is added. Then, a basic global illumination algorithm is implemented using the Lambert BRDF and next event estimation. Finally, post-processing is discussed. The second lab covers even more advanced topics. The Cornell box from the first lab is extended with area lights, soft shadows, sampling, and anti-aliasing. Finally, we set up a weighted-style ray tracing demo scene where we implement procedural textures, glossy reflections, and refraction. We emphasize on the fact that all these effects are very hard to implement in rasterization and how ray tracing allows us to generate these pretty pictures in an elegant manner. When designing the graduate course, our main concern was with the fact that we wanted to incorporate a wide range of topics and accommodate varying students' background. In terms of ray tracing alone, we also had to cover a lot of ground, including basic ray tracing concepts, light transport theory, and path-based sampling. These will have to be combined together with rasterization, visualization tools and techniques, virtual reality technologies, graphics applications, etc. Rayground helped us even more when designing the Graduate Lab course. We devoted 4 2-hour labs to ray tracing. The first 2 labs covered the same topics as the Undergraduate Labs in order to get unacquainted students up to speed. Lab 3 continues with more advanced topics like visibility determination, ambient occlusion, physically based BRDFs, and important sampling of BRDFs. Finally, the 4th lab introduces multiple important sampling, path-based sampling, scattering events, phase functions, and volumetric light transport. The introduction of Rayground was an exciting and productive experience for both instructors and students. Most students quickly caught up with the API and the mechanics, which they found very intuitive. Both as an interactive platform and a companion tool for lectures, it helped them understand fundamental concepts better and inspired them to experiment further with ray tracing. A lot of them were instantly drawn to ray tracing's elegance and potential for realistic image synthesis compared to rasterization. Rayground cannot yet accommodate certain fundamental computer graphics concepts, mainly due to the current status of web-based graphics technology. 2 of our major concerns include animation systems and bidirectional methods, which are instrumental to image synthesis. We're also looking forward to a broader case study and the continuous evolution of courses based on Rayground over the coming years. As a closing note, we believe that Rayground can be more than an educational tool. It can serve as a community hub for ray tracing related subjects where people share, develop, and publish ideas. The high availability of the web makes it a suitable place to present best practices and propose new methods. Standard algorithms like BRDFs, light sampling, filters, denoisers, and others can be made indexable and reproducible for everyone online. Thankfully, technology is also advancing, with WebGL support constantly improving and the new WebGPU specification for accelerated graphics and compute on the web on its way. We're working towards a major release very soon. Thank you very much.